Okay, welcome back. So we're just going to start where we left off. So looking at number 12, looking at part A, we want to find the domain of this function using interval notation. So as mentioned last time, our domain is valid for everywhere that we don't have a vertical asymptote. So particularly, if we look at right here, we have a vertical asymptote, so our function gets really, really close to it without actually ever touching that vertical line. And the same thing on this side. We also have another vertical asymptote. It may be a little bit harder to tell for this one, but our function gets really close to this line, but doesn't actually touch it. So for this function, let's see, we want to find the domain. We know from this that x cannot be equal to -2, and x cannot be equal to +2. Everything else is fair game. So when we write this in interval notation, we have from -infinity all the way to -2, but then we have to jump over that vertical asymptote. So we do a union, -2 to +2, but then we have to jump over that asymptote, and then 2 to +infinity. So this is the domain for our function. Now what about f of 9? We want to find what f of 9 is. Well, f of 9 is basically just saying, well, what is the y value when x is equal to 9? So we can count on our graph. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that is this point right here. So when x is equal to 9, the y value is equal to 1. We want to find the y-intercept. The y-intercept is where this function touches the the y-axis. So that would be this point right there. And so I am going to write this as 0, -2, because that is that point right there. 0 for the x and -2 for the y. What about the x-intercept? This is just where our function touches the x-axis. The only point that that happens is right here. So we would say this is the point -1 for the x, and for y, this is 0. So this is our x-intercept. What about the intervals where f of x is increasing? So just a quick reminder about increasing. If we have a function that is going up like this, look at any part of the function, start like right there, and as we go to the right, is it going up or down? We had to go up. And if we go to the right, we had to go up. Right, up, right, up, right, up. So every increment that we go to the right, we're going up on this function, so it's increasing. What if we have a function that looks like this? Well, every time we go to the right, we have to go down. Right, down, right, down, right, down, right, down, right, down. So this is decreasing. And so for any function, even if it's doing some crazy stuff, we can always figure out where it's increasing or decreasing just by evaluating as we move to the right, are we having to move up or down? So over here, right, up, right, up, right, up, right, up, right, up. And then notice around right here, if I move to the right, now I have to go down to get to our function. Right, down, right, really far down. Right, down, right, down, right, down, right, down. And then about right there, if you go right, up, right, up, right, up, right, up, right, up, right, up, right, up. So we can see that our function on these intervals right here is increasing over here, decreasing over here, and then increasing again over here. So with that little refresher, now let's look at our function and see if we can find where it's increasing. So increasing, well, starting from over here, as we move right, we have to keep going down to get to our y coordinate. So right down, right down, right down, right down. So all of this right here, it is decreasing. Okay, so no intervals of increase over here. What about over here? Starting right here, if I move to the right, I have to go down, right, down, right, down, right, down, right, and keeps going down. So this is also decreasing right here. What about right here? Right, down, right, down, right, down, right, down, right, down. And it's slowing down, but it is still going down forever and ever on this interval. So there are no intervals where this function is increasing, because we just showed that it's decreasing everywhere on its domain. And so for the next question, where we state where f of x is decreasing, it's decreasing on its entire domain. So we would rewrite that as negative infinity to negative 2, from negative 2 to positive 2, and from 2 to positive infinity. We don't include our vertical asymptotes as a part of increase or decrease. So we only have our domain to work with. So even if the function is decreasing on the entire domain, we still have to exclude negative 2 and positive 2. Let's move over here to part G. We want to find what happens as the limit of f of x goes, or the limit of f of x as x goes to positive infinity. So as x goes towards positive infinity, that's as x goes that way. Well, it's tapering off. It's getting flatter and flatter and flatter. And it's between 1 and 0. So it's probably some value in between that. But you can kind of get a hint from, if you look at the if you look at the value that it's approaching over here. Over here at negative infinity, this is from negative 1 to 0. Usually the asymptote is going to be halfway in between, or the end behavior, what value it's approaching, is going to be some value in between those two. And it's usually best if we have well, in fact, it is definitely best if we have an actual function rule that defines this. It'd be easier to confirm that. But it is approaching 0. And the same thing as x goes in the negative direction. As x goes towards negative infinity, our function, the y value, is approaching 0. So for part H, as x increases without bound, so x increases without bound, all of this means as x goes towards positive infinity. So what is our function doing as x goes towards positive infinity? It approaches 0. And what about over here? As x decreases without bound, that means as x goes towards negative infinity. And what is our function doing as we go towards negative infinity? What is the y value approaching? Well, we already determined that up here. It also approaches 0. Next, we want to estimate the point of inflection. So remember, the point of inflection is where our concavity changes. So concavity, on the other hand, if we review that for a second, if I have a function that looks like this, let's look at the slopes here. The slope here, if I estimate it, is probably like positive 2 there. And over here, the slope's probably 1. Over here, the slope is flat, m is equal to 0. Over here, it's probably negative 1. And then, at some point, right around here, the slope starts going in the opposite direction. It starts increasing. So over here, the slope was decreasing. We went from 2 to 1 to 0, negative 1. And then around right here, the slope starts at negative 1 again, but then it goes to flat, m equals 0, m is equal to 1, m is equal to 2. Our slopes start increasing right here. We have negative 1 to 0 to 1 to 2. And our inflection point is where the concavity changes. So over here, we were concave down, and over here, we were concave up. So our inflection point is where the concavity changes, and we use a point for that. Or we list a point for the point of inflection. So we want to estimate the point of inflection for this function. Well, let's see. Our function, the slopes, the rates of change are pretty flat, but they're negative. And then as we get further and further in the positive x direction, they start getting more and more negative. So it gets relatively flat over here, and then it gets steeper and steeper and steeper. The slopes are decreasing on here. For the whole part of this function, it's all concave down right here. But what about over here? Our slopes are really negative, but they start increasing and going a little bit up. Now they don't go positive, or they don't even go flat, but it is concave up right here because the slopes start off really, really negative, and then they start to flatten out a little bit. But then it transitions to going kind of flatter, but still negative, to again going really, really negative down there. So around right here, we had a transition from concave up, where our slopes were increasing, to concave down, where our slopes were decreasing. So point of inflection would be 0, comma, negative 2. And over here, we don't have any inflection points because the slopes start off really negative, and then they just start increasing the whole way over there until it just flattens out towards positive infinity. But the concavity never changes when we're doing that. So we only have one inflection point at 0, comma, negative 2. What about the horizontal asymptote? Do we have one here? Well, as x goes towards positive infinity, we've already determined that that is 0, and x goes towards negative infinity, it's also 0. So our horizontal asymptote is y equals 0. Next, we want to find the average rate of change over the interval from negative 1 to 0. Remember, our rate of change formula is f of b minus f of a divided by b minus a. And intervals like this are always in the form of a comma b. So really what this means is we want to find f of 0, because that's our b, minus f of negative 1 divided by 0 minus negative 1. Well, even though we're not given a function rule, we do have we do have a graph, which is going to be pretty useful for us, because f of 0 just means, well, what's the y-coordinate when f is 0? Well, the y-coordinate when f of 0 is 0. I'm sorry, not 0, negative 2. So this is equal to negative 2. Kind of running out of room here, but that's my fault. I wrote this off into the middle. So negative 2 is f of 0 minus f of negative 1. So what's the y-coordinate when x is negative 1? When x is negative 1, it's 0. So negative 2 divided by, or negative 2 minus 0 divided by 0 minus negative 1, which really just means plus 1. And so, simplifying this, we have negative 2 divided by 1, which is negative 2. So that is our average rate of change over the interval from negative 1 to 0. Lastly, we want to find the intervals where f of x is less than 0. That just means, where is our function below the x-axis? So let's look at this. And I'm going to use a green pen so that we can differentiate it from everything that I've written in red. So the x-axis is this line right here, right? So our function right here, is it above or below the x-axis? Well, I'm just going to highlight in green where it's below the x-axis. So over here, this is all good, because that's below. This is what we want. This is what the question is asking. All of this is good. It's all below the x-axis. And then over here, this is above. All above, 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 above. And then right there, at x equals negative 1, it dips below, so I'm going to start highlighting that again. So all of this is below. That's good. And then over here, this is all above, 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 above. It stays above for the rest of the function. So really, the only part of our function that is actually below the x-axis is all of this right there. And so now we just need to find intervals for that. Well, this starts all the way at negative infinity, and it goes all the way to the asymptote right here, which is at negative 2. And then it dips below again right at this point. Well, this point is right at negative 1, where x is equal to negative 1, and it stays below all the way until the other vertical asymptote at positive 2. So stitching all of that information together, we would say that our interval where f of x is below 0 is from negative infinity to negative 2, and then union, because we have to jump over this little area of the asymptote and then this portion where the graph is above 0, start at negative 1 and then all the way to 2. And so, there we go. We have from negative infinity to negative 2, union negative 1 to positive 2. Last question regarding this graph is, what could be a denominator for the graph above? And we're told that this is a rational function. And remember, our rational functions, r of x is equal to f of x divided by g of x. For all of our rational functions, our domain is only defined where g of x is not equal to 0. So, if we look at our graph, notice that we have these vertical asymptotes at negative 2 and positive 2. So, we know that our function cannot be defined for negative 2 and positive 2. That means that whatever this function is for g of x can't be equal to, when we factor it, it can't be equal to negative 2 and positive 2. So, x can't be equal to negative 2, x can't be equal to positive, or negative 2. So now, we have to figure out which of these functions has solutions of -2 and +2. So really there's two directions you can go to solve this. You can either factor these and figure out which ones have solutions at -2 or +2, or since you know that you can't have these values, you can write it as x minus 2 times x plus 2 can't be equal to 0. It's like we're working backwards on the factoring. And if we multiply these two together, if we FOIL them, we have x times x, which is x squared, x times 2, which is plus 2x, -2 times x, which is minus 2x, and then -2 plus 2, or -2 times +2, which is -4. These two terms here, our linear terms, will cancel out, and all we're left with is x squared minus 4. So, our answer is C. The other route that we could have gone with this is factoring all of these. This one, if we factor it, will give us x plus 2 times x plus 2. And we know that from this, we need a +2 and a -2. Well, we have a -2 that x can't be equal to over here, but we don't have a +2 because these will both be x can't be equal to -2. So this can't be our answer. For B, if we factor this one, we have x minus 2 times x minus 2. Same issue that we ran into with answer A, so that can't be it. If we factor this, we can use the property that a squared minus b squared is equal to a minus b times a plus b. So if we were to factor this one, we would see that we have x minus 2 times x plus 2. And then that's what we have over here. So if we were working from the answers that we have, we would know that once we solve this using our zero product property, that C would be our answer. And similarly for D and E, they both can't be the correct answer because this is just saying that x can't be equal to +4, and E is saying that x can't be equal to -4. So that's how we could eliminate D and E. So you can choose to approach this however you like. Personally, I prefer to just work with what we know g of x can't be equal to, and kind of work from, I prefer to work backwards on this one instead of factoring all of our answer choices. So, lastly, let's look at the test prep questions. So for number 14, we have this function r of x is given by f of x divided by g of x. And we're given that f of x is equal to this and g of x is equal to that. So if we write that out, f of x is equal to x squared plus a squared, and g of x is given by x squared minus a squared. And we're trying to find the domain of r of x. So our domain for r of x is going to be defined everywhere except where our denominator is equal to 0. So we're saying that our denominator, x squared minus a squared, cannot be equal to 0. And when we're interested in finding the domain, we don't even care what the numerator is doing. We can ignore that. So let's just figure out where our domain is restricted. So we can factor this, as seen on the previous page, we can factor this as x minus a times x plus a can't be equal to 0. And using our zero product property, we have that x can't be equal to positive a, or x cannot be equal to negative a. And so, if we were to plot this on a number line, we have negative a here, we have positive a here, and we have open circles on positive and negative a, but our function is fine everywhere else. Our function is defined everywhere except negative a and positive a. And so if we were to write this in interval notation, So from negative infinity all the way up to negative a. That's good. But we have to jump over negative a, so we go to the other side. We have our union symbol, open parentheses, negative a. All of this is fine up to positive a. Jump over positive a onto the other side of it, so union, open parentheses a, and then to positive infinity. And so that matches answer C perfectly. So I have to go to a meeting, so I'm going to do that real quick, and I'm going to pause the video.